Hello everyone. So this tutorial is going to build on the previous tutorial where we discussed the writing of net ionic equations. However, all of those reactions that we studied in the last tutorial were all precipitation reactions. And those precipitation reactions are not the only reactions to which net ionic equations apply. And so in this tutorial, we're going to turn our attention to neutralization reactions. Now, by definition, neutralization reactions are those reactions that occur between an acid and a base. However, there are different types of acids and bases. There are strong acids and weak acids, there are strong bases and weak bases, and they don't behave the same chemically. And so if we're going to understand neutralization reactions, then one of the first skills that we need to develop is the ability to tell the difference between a strong acid and a weak acid and a strong base and a weak base. Well, as it turns out, that's actually not that unwieldy. Essentially, you have a very small number of strong acids, and those strong acids are hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, chloric acid, perchloric acid, and sulfuric acid, as long as we're talking about the first ionization. Now, what I mean by that is sulfuric acid has 2 protons that may be donated. And so the first ionization removes one of those 2 protons that can be donated. So the first ionization ends up giving you a species that looks like this. And the second ionization involves this particular anion, which then falls apart to give you yet another proton and the sulfate ion. And so when I'm discussing the first ionization of sulfuric acid, I mean the first of these processes that I've just shown you. Now, as it turns out, strong bases are also somewhat easy to identify. They are the hydroxide salts of group 1 metal cations, so things like sodium hydroxide, potassium hydroxide, and so on down the rest of group 1 when we're looking at the group 1 metals, and also any soluble group 2 metal hydroxide salts. And so if you think back to the solubility rules, basically the soluble group 2 metal cation salts would involve calcium, strontium, and barium, but not magnesium. And so these salts, so that would be barium hydroxide and strontium hydroxide and calcium hydroxide, would also be considered strong bases. Now, we'll actually have to take a couple of examples in order to understand how the neutralization of strong acids and strong bases differ from when we have weak acids or weak bases involved. So let's jump right into it. And right here we have this example where we're being asked for the balanced molecular and also the net ionic equations for the reaction between hydrochloric acid, which is a strong acid, and barium hydroxide, which is a strong base. And so if we start piecing together the molecular equation, so we have hydrochloric acid and barium hydroxide, both of these in solution. Okay, it's up to us now to predict the products. And much like the precipitation reactions that we were discussing in the previous tutorial, the neutralization reactions are also double displacement reactions. And so I would switch the anionic and cationic components of each of these reactants, and that should give me the products. And so I should get barium chloride and the other product should be water. Now, again, it's not enough to know the identity of the products. We also have to know about their states. Well, water is a liquid if we carry this out at room temperature, and we haven't been told otherwise, so that's the assumption we're going to go with. Barium chloride, right? Chlorides are typically salts that are soluble, okay? Now, the only exceptions to chlorides being soluble is if we have silver, mercury, and lead salts of chloride compounds. And so, since barium is not any of those three exceptions, then barium chloride should be soluble. Now, let's check to see if the equation is balanced, and right off the bat I can tell it isn't, because basically we have two chlorines here where we only have one on the other side, and so that means I need a coefficient of 2 in front of the hydrochloric acid. But then that throws off my hydrogens, right? Because there are 2 hydrogens here, but 2 there, so 2 plus 2 would be 4, and I only have 2 hydrogens here on this side. And so that means I need a coefficient of 2 in front of the water. So checking to see if things are balanced now, I have 4 hydrogens on either side, 2 chlorines on either side, 1 barium, and 2 oxygens, so this equation is now balanced. All right, now that we have the balanced molecular equation, now I can start thinking about piecing together the net ionic equation. And so if you recall, essentially you're going to take all of the species that are involved in the reaction that are in aqueous solution, and you're going to break them apart to their component ions. And so hydrochloric acid would be the hydrogen ion and a chloride ion. However, there was a coefficient of 2, so I should have a coefficient of 2 in front of both of those ions. Then barium hydroxide, well, that would give me barium 2 plus and the hydroxide ion, but there were 2 hydroxide ions present in the balanced molecular equation, so I need 2 hydroxide ions when I start to piece together my total ionic equation. The barium chloride is also an aqueous solution, so barium 2 plus, and then 2 chloride ions. And then lastly, recall only those substances that are in aqueous solution get separated into their constituent ions. Water is a liquid, not an aqueous solution, and so I would keep the formula for the water molecule intact as a liquid. Now I'm going to cancel out my spectator ions, and so the barium is a spectator ion, the chloride is a spectator ion. So if I write out what's left, basically that gives me 2 hydrogen ions plus 2 hydroxide ions. That's going to give me 2 moles of water. However, if you notice, there is a common coefficient of 2 in each of these terms, and so that reduces out, and I get hydrogen ion in aqueous solution plus hydroxide ion in aqueous solution, and that's going to give me a mole of water. Now, as it turns out, this net ionic equation is actually pretty typical of strong acid, strong base neutralizations. But what happens when one of the species, or the acid or the base, turns out to not be a strong acid or a strong base? What if it's a weak acid or a weak base? Well, let's see how that would actually work out. Suppose that I take a solution of calcium hydroxide and carbonic acid and mix them together. And I'm going to do the same. I'm going to write the balanced molecular equation and also piece together the net ionic equation for this reaction. So, following the same procedure that I used in the previous slide, I'm going to start piecing together the balanced molecular equation. So that's calcium hydroxide and carbonic acid. And again, there's no mention of either of these being in a specific phase, and so we're left to assume that these are each an aqueous solution. Now, I have to think about what the products would be. Well, I'm going to exchange the anionic and cationic components of each of these reactants, and I'm going to get calcium carbonate and water. Okay? Once again, water would be a liquid. Carbonates are typically not soluble. So if that's the case, I have to check the exceptions, and the only exceptions are ammonium cation salts or alkali metal cation salts. And calcium is not an alkali metal, it's an alkaline earth metal. And so as a result, that doesn't qualify as an exception, and so that would mean that this carbonate still is insoluble, and so that would be a precipitate. Now, remember, the way that this works is anything that is in solution that ionizes completely gets broken apart into its ions, but remember that carbonic acid is not one of our strong acids, it's a weak acid. And so it doesn't dissociate completely. And since it doesn't dissociate completely, then I cannot break it apart into its component ions. And so the only thing that I can break apart into its component ions would be the calcium hydroxide. So I would have calcium 2 plus 2 hydroxide ions. That's going to be combined with carbonic acid to give me calcium carbonate and water. Now let's check to see if things are balanced. All right, I have 1, 2, 3, 4 hydrogens on this side. Over here I only have 2, so that needs a coefficient of 2 here. All right, if I do that, I'll have the 4 hydrogens I need, but I'll also have 5 oxygens. So 2 oxygens here plus 3 is 5. 2 oxygens here plus 3 is 5. I have 1 carbon. And I have a calcium and a calcium. So that's actually balanced now, but then this coefficient of 2 would also have to be included down here as I start to piece together my net ionic equation. Now, at this point, I've broken down everything that I can break down, going from my molecular equation to my total ionic equation. Okay. However, if we look carefully, there are no spectator ions. Basically, the calcium ends up associating with the carbonate to give me the calcium carbonate, which is a solid. The hydroxide associates with the hydrogen ion in the carbonic acid to give me the water, which is a liquid. And so as a result, nothing cancels. So I have calcium in aqueous solution, hydroxide ion in aqueous solution, carbonic acid in aqueous solution, giving me calcium carbonate and 2 moles of water in the liquid state. And so since nothing cancels, then believe it or not, even though this is the total ionic equation for this particular reaction, it also happens to be the net ionic equation as well in this particular instance. And so in class tomorrow, we're going to take more of these examples. We're probably also going to discuss how sometimes these neutralization reactions may also produce gases, as well as liquids and solids, as we've seen in these particular examples that I've given you today. And so you do much the same thing. You go and you break apart and dissociate what you can if it's an aqueous solution and it's a strong electrolyte, basically a strong acid, strong base, or the salt of an ionic compound. And those things that do not meet that definition do not get dissociated, and then you cancel any spectator ions that you can possibly cancel. So we're going to do more of this tomorrow. Again, I'll check in with you guys as you work on your assignment as you walk into class. If you have any questions, by all means, email me or speak to me in class, and I'll see you guys tomorrow.